It is my pleasure to present to you today an overview of the work carried out by RILEM TC 281 CCC over the last 6 years. I'm Nele de Belie, professor at Ghent University, RILEM president-elect, and I have been chairing this TC together with Susan Bernal. In many regions worldwide, severe efforts are made to combat global warming. Since the production of cement contributes to around 8% of the global CO2 emissions, the concrete and cement sector have set goals to lower the carbon footprint. And since the emissions are largely related to the decomposition of calcium carbonate in the clinker kilns, the use of supplementary cementitious materials to replace part of the Portland clinker can be an important part of the solution. Actually, the use of SEMs often contributes to pore refinement at later ages and can result in improved durability of concrete in several aggressive environments. However, in carbonation-prone environments, we have to consider that the carbonation rate is increased due to the reduced amount of Portlandite that could act as a buffer against CO2 penetration. Here in our previous research, we have shown that, for instance, in mixes with increasing amount of fly ash from 0 to 67% of the binder content, at early ages, there might be an increased amount of Portlandite production due to the stimulating effect on the clinker reaction. But after about 2 weeks, the pozzolanic reaction kicks in, and after more than a year, it can be that the Portlandite content goes down to 0. Hence, there can be an increased risk of reinforcement corrosion induced by carbonation. Therefore, within the RILEM Technical Committee, CCC, we have formed 6 working groups to study various aspects of carbonation of concrete with SEMs. The first 2 working groups have focused on the carbonation mechanisms, and the first we have done was to compile an extensive literature review, elucidating the effect of SEM characteristics, exposure environments, and curing conditions on carbonation. Here you can see that the thermodynamic modeling is showing from the right to the left how the phase assemblage of a white Portland cement paste changes as a function of the amount of CO2 that has reacted. And in the right-hand figure, you can see the corresponding decrease of the pH and of the calcium silicon ratio of the CSH. So as you can see here, Portlandite is the first major hydrate that decomposes to calcium carbonate, to calcite. And that leads to a moderate volume increase of about 12%, while the pH is remaining stable around 12.5. Then actually it's the CSH that starts to decalcify down to a calcium silicon ratio of about 1.3. And then we have monocarbonate that decomposes to stratlingite, and the decalcification of the CSH continues down to a calcium silicon ratio of about 0.75 and a pH of around 11. And then stratlingite and ettringite decompose, and the CSH decalcifies to the calcium silicon ratio of around 0.67, while the pH is further lowered to 10. And then finally, the CSH is decomposed completely into calcite and silica gel, and the pH drops rapidly further to 8.5. Well, actually, the same carbonation sequence is observed in Portland cements blended with different types of SEMs. However, with the reduced content of Portlandite, carbonation more rapidly affects the CSH and the cache phases, and this contributes to a coarsening of the pore structure, whereas in normal Portland cement paste, rather a pore consolidation of smaller pore structure is created. We can also see that in reality, the Portlandite carbonation may be incomplete due to covering by calcium carbonate crystals, slowing down the further carbonation reactions. Now, as the carbonation reaction proceeds with the square root of time, the first equation here assumes a steady state condition. However, like mentioned, if carbonation reaction products block the pores, and because of continuing hydration, the carbonation coefficient, K, could actually decrease with time. And then in the second equation here, you would have here a negative exponent N. On the other hand, N could be positive when the material is drying out or it cracks due to carbonation shrinkage. And that is often what we see in the case of concrete with supplementary cementitious materials. For the phase assemblage, we can look to ternary diagrams. So here the regions are highlighted corresponding to the major SEM groups. And on the right, we can see the different hydrate phases. So this shows the broad range of compositions that can form as a function of the type of SEM that is used. The higher amount of alumina contained in SEMs will influence the composition of the cache phases. And this has been found to lead to faster carbonation. Also, we see that the percentage of the calcium carbonate that is present as calcite is reduced, while we have an increased amount of the metastable aragonite and vaterite. And this might lead to a higher permeability. But on the other hand, there could be secondary reaction products, such as layer double hydroxides, which may improve carbonation resistance. But yeah, their effect is not yet fully understood. Now, how can we estimate carbonation resistance of a certain mix? In the past, this was often done just based on compressive strength or permeability. However, this is ignoring the CO2 binding capacity. To overcome this, in a first approach, the carbonation rate can be related to the clinker content and the water binder ratio. This is quite simple to apply, but it neglects the buffering capacity of the specific type of SEM and the alteration in the pore size. Then secondly, we can use the K-value concept, where we replace the water-cement ratio by an equivalent water-cement ratio, in which we express the activity of the SEM as a fraction of the activity of Portland clinker. This is, of course, less simple because you have to know actually these K factors for each specific SEM. And then thirdly, we could use the buffering capacity approach, where we use the water over reactive calcium oxide as the main indicating factor. It's most scientifically sound, but then you have to know or calculate this reactive calcium oxide content, and that may not be so simple. But it is easier with this approach to include new materials or to apply it also on new materials. Still, the effect of the alteration of porosity is in this way little accounted for. Some other important factors like curing is of course very important to limit carbonation. We also know that carbonation is proceeding the fastest at intermediate relative humidity levels, but it's not very clear if the range is the same for concrete with SEMs as for ordinary Portland cement concrete. And then temperatures, higher temperatures generally accelerate carbonation as the chemical reactions and diffusion will occur faster. What about CO2 concentration? Well, increasing this concentration is a common approach to accelerate carbonation for testing. And from a thermodynamic viewpoint, actually, it should not change the phase formation at all. But there are various side effects, as mentioned here. For instance, more than 10% CO2 would lead to an incomplete reaction of the Portlandite due to fast calcite precipitation at the surface. Also, CSH carbonation rate increases with CO2 concentration. So there would be more calcium carbonate formed from CSH versus Portlandite. So you have a change in proportions. And also the polymorphs found may be different at higher CO2 concentrations. Also, at higher CO2 levels, the release of water during the carbonation reaction will go faster. And actually this water in the pores can slow down further carbonation. So normally the increase in carbonation coefficient with the carbon dioxide level is lower than expected from the square root law that we would normally theoretically apply. So to obtain further insights in all these processes of carbonation of concrete with SEMs, we have conducted an extensive interlab test, which took us about 4 years, with 22 participating laboratories. We have compared carbonation of mortar and concrete with the 3 common cement types, CEM1, CEM2, CEM3, both in accelerated and natural carbonation conditions. And the specimens were either sealed cured for 28 days and then preconditioned at 28 days in the same conditions as in the selected standard, or they were completely tested according to one of the selected standards. We compared 9 different standards, like you can see in this table, the specific curing conditions, preconditioning conditions, and carbonation exposure conditions. And for instance, for the percentage of carbon dioxide, it varies between 1% over 2, 3, 4, 5% up to 20%. The mix design and the curing conditions were such that the mortars or concrete samples were all of similar strength and consistency, independent of the cement type, actually. And the result showed, fortunately, that the different standards for accelerated carbonation were mostly able to rank the 3 cement types in the same order. So actually, the slowest carbonation for CEM1, followed by CEM2, and then CEM3 had the highest carbonation rate. Nevertheless, the coefficients of variance for repeatability and reproducibility in labs and between labs were quite high. We also tested under natural carbonation conditions, and then we did obtain more or less the same order for carbonation of the different cement types, both for indoor and sheltered outdoor conditions, and both for mortar and for concrete. And when we looked at calculation of carbonation rates, it seemed essential for natural conditions that the exposure period was at least 1 year to reach a constant carbonation rate. Regarding the impact of curing, we found a significant difference between water and sealed curing, with sealed curing resulting in higher carbonation depths, and as expected, a reduced curing time resulted in higher carbonation depths. Unexpectedly, the impact of curing on resistance to carbonation seemed larger in the case of CEM1 compared to CEM3. In these results of accelerated testing, you can see a trend that the carbonation depth increases with increasing carbon dioxide concentration. But actually, the reproducibility error between the labs was so large that this effect was not significant. We have also compared the carbonation rate of mortar and concrete. And actually, the carbonation coefficient of concrete was 1.18 times the one of mortar, with the aggregate to cement factor being about 1.8 times higher for concrete than for mortar. And actually, in a natural carbonation test, the same factor was obtained. We then also tried to correlate the accelerated with the natural carbonation conditions. And theoretically, if you look at the square root of concentration relationship with natural carbonation CO2 values of 0.04%, and then for accelerated carbonation, for instance, 1%, we would obtain a conversion factor of 0.2. And for 3% in accelerated conditions, it would be 0.11. However, in reality, for instance, here in sheltered outdoor conditions, you see that the actual coefficients were quite a bit higher. So this means actually that the theoretical relation would lead to an underestimation of the real natural carbonation rate if you start from accelerated tests. Now, apart from our own round-robin test, we also established an extensive database of more than 1,000 mixtures with carbonation results from literature, and included commercial binders with Portland cement and different SEMs, and also different binary and ternary blends with SEMs. And we have registered a range of different variables like chemical composition, setting times, activity, and indices, and so on. For the evaluation of the data, so we calculated carbonation rates based on the provided data points. And if the obtained regression had a negative intercept, this was actually set to 0 because this is physically not possible. Now, the effects of the binder composition and the mix design, curing and preconditioning, and relative humidity on the carbonation rate were all evaluated, and also possible correlations between compressive strength and carbonation resistance. Now, we found indeed that the water over reactive calcium oxide ratio is a decisive factor for carbonation resistance. And that was the case for different types of binders. It was also seen that concrete with higher compressive strength tended to exhibit a higher carbonation resistance, so including this factor in a model might also help to estimate the carbonation rates better. Therefore, the strength was also included in a probabilistic model, and you can see here all the different parameters that were included, and the different coefficients here were then calculated with this probabilistic model. So for instance, it was seen that the calcium oxide reactive needs an exponent F, and this exponent F is considerably less than 1, as you can notice here. The relation between accelerated and natural carbonation is seen here in the exponent D for the CO2 concentration. That is also less than 0.5, and the 0.5 would be the square root behavior. However, for the time, the T here, the exponent E, is very close to 0.5, so there the square root relation is quite well followed. We have also applied machine learning, which indicates that curing time could be used as a parameter to further refine the estimation of the carbonation depth. Actually, carbonation data were also analyzed in a database specifically for alkali-activated cements by working group 6. And here the analysis indicated that a better indicator of carbonation resistance would be the ratio of water over calcium oxide plus equivalent magnesium oxide, sodium oxide, and potassium oxide amounts, because also these are able to bind CO2 similar to calcium oxide. However, the scatter of the data was quite significant. Working group 4 carried out an additional interlab test to study the combined action of carbonation and mechanical loading, and they also made a recommendation that can be consulted in materials and structures. The results here indicated that the carbonation depth is lower in the case of a limited compressive load, like 30% of the failure load, and that is actually because of poor compression. Whereas if the load is increased to 60% of the failure load, there is also an increase of carbonation rate because some damage and micro cracks start to occur. And this effect is actually similar, independent of the presence of blast furnace slag or fly ash in comparison to Portland cement mixes. If we consider tensile loading, the carbonation depth actually increases with a factor of 0.5, 0.8, as the load level increases to 60% of the failure load. And this is again the same for different SEMs and also for different percentages of CO2. So anyway, this makes clear that it is very important that the loading conditions in a real structure are considered if you want to make an accurate estimation of the carbonation progress. Finally, working group 5 made a critical review of the effect of carbonation on reinforcing steel corrosion. So whereas carbonation itself has been a research focus already in a lot of projects, the possible results of carbonation, like corrosion and actually damage at the structural level, have received little research attention up to now. And actually, these have more relevance in practice. From observations of more than 200 cases in Switzerland and Japan, it seemed that in only 10 to 15% of the cases where carbonation depth exceeded the cover depth, so there was carbonation, but actually there was only relevant damage in 10 to 15% of those cases. So this means that maybe it's more important to look really at the damage and not only at carbonation itself. And this can be understood because we know that carbonation proceeds the fastest at these intermediate relative humidity levels, whereas actually in these cases, it seems that the corrosion rate would be rather low. It's only at high relative humidity or in contact with liquid water that severe corrosion damage is expected. So apart from the effect of the exposure climate, the cover depth and the pore structure are important influencing factors that affect the moisture state at the steel surface and hence also the corrosion rate. So we have to conclude that the fact that the reduced pH alone is not sufficient to lead to a significant steel corrosion suggests that the focus should shift from studying carbonation to actually studying corrosion of the steel in carbonated concrete. And that should then allow to conclude if faster carbonation of concrete with supplementary cementitious materials would also mean a higher risk of damage in concrete structures. With this, I want to conclude, and I want to thank all members of the TC281 CCC for the very fruitful collaboration. And this collaboration has also resulted in a topical collection in Materials and Structures and a review paper in RILEM Technical Letters. So if you want more information, can be found there. Thank you for listening.